Hello everyone, this is Ashoke, your personal guide and mentor. I welcome everyone to my YouTube channel AKB Tutorials. Here we are going to discuss and cover some important concepts of mechanical engineering that are very useful and helpful for competitive exam and job interviews. So let us start today's session. Hello everybody, welcome back to my channel. Now before starting I am going to just discuss something that is for previous videos. If you want to refer previous videos, and you can go to the description box, so where the links are given for better understanding of the subject. So please refer previous videos, and today we will start our new topic. Our today's topic is stress strain diagram. So it is one of the most important topic as far as mechanical engineering is concerned. Now, what is actually the stress strain diagram? Now, this is the result of tensile test when plotted on a graph paper. So, for time being, consider a body is under tensile load. Now, once the load is applied over the body, say P is the load applied over the body, P is tensile load. Now, if this kind of load is applied over the body, some deformation will take place. This is the deformation dl produced for a length of say L0. L0 is the original length or gauge length of the body, and dl is the extension produced in the body under load P. Now, the stress developed, or that is called engineering stress, that is equal to given by P by A. Say the area of cross section is circular, say the diameter of this bar is D. So area of cross section is given by pi by 4 D square. So if we divide the external load, or the resistance developed also is equal to the external load, that is the resistance developed P divided by the original cross sectional area pi by 4 D square, then it will give the engineering stress. Similarly, we can get strain. It is given by say epsilon, that is the linear strain, is the longitudinal change in length, that is dl to original length. So this is the engineering strain. So whenever a body is loaded with external load P, say cross sectional area is given by A, then we can easily calculate what is called sigma and epsilon, means what is the stress developed in the bar as well as the strain. So now we will see here stress strain diagram. So before that, we are going to discuss what is called a tensile test, or it is called simple tension test. Simple tension test. So in this test, a standard test specimen, so we will come down to standard test specimen. So a standard test specimen is tested in a machine. That machine is known as the universal testing machine. So the standard test specimen is attached to that UTM machine, that is universal testing machine, and the machine is switched on. Thereby a gradual load is applied over the specimen. Slowly the specimen will increase in its length because of tensile load is applied, and this test is carried out up to the breaking of the specimen. Now if we see what is called, that is standard test specimen. So this test is carried out on a standard test specimen, means whatever may be the material, but the test is carried out on a specimen whose shape and size are fixed. Okay, so this is the standard test specimen. So at the end the diameter is more, after that the diameter is less, and it will remain same throughout. Okay, so at the end if you find, you will see that more diameter, and at the center the diameter is uniform diameter. And before testing, 2 points are marked here. This length between these 2 points is called the gauge length, or is called L0. So as we have considered. Okay, so L0 is known as the gauge length over which the test is carried out. So before testing, we are measuring this length L0, that is gauge length, or is known as original length on which the test is carried out, and D means the diameter, initial diameter of the specimen. So at the end the diameter is more for gripping purpose, and also there is a radius here, so you can see. So this specimen is called standard test specimen and is given by L0 is equal to 5 into D0 for a circular specimen. So if this one is circular, say this one is circular, the bar is circular bar. So for this L0 is equal to 5 into D0. If it is a square bar, then the formula is L0 is equal to 5.65 root over of A0. So this specimen is known as standard test specimen. So whatever may be the material, when testing is to be carried out, so this size and shape to be used, that is called standard test specimen. And this test specimen is attached in that machine is called UTM machine. So there are two jaws, upper jaw and lower jaw. Say these are the two jaws in which the specimen is fitted. The specimen is fitted here. Okay, so in the machine, that is UTM machine, that is called universal testing machine, in that machine provision is there so that with the help of hydraulic force the load is applied over the body and this lower jaw will come down, upper jaw will remain in a fixed location and the lower jaw will come down slowly. Thereby the member will extend in its size, and that extension is measured with the help of an instrument that is called extensometer. So with the help of extensometer we can measure the extension produced in the body under load. Say P is the load applied. Initially P value was nearly 0 and slowly it will increase to a maximum value. So this P will carry on increasing until the specimen fails. So once the specimen fails, the test will be over. Okay, now we will note some points. Say initially the load applied over the body is P1. P is gradually increasing. Say the second point where we have noted is say P2, then P3, number of points, and at last we have noted Pn load. So that means this is the load applied over the specimen and we have noted from the gauge installed on this machine. So the gauge installed in this machine, so from that we have noted P1, P2, P3 dot Pn values, means n number of points we have noted. And with the help of extensometer also we have measured the extension. Say at this point the extension was dl1. At this point when the load is P2, say the extension is dl2, and at this point when the load is P3, say it is dl3, and when the load is Pn, so let the deformation is, so this is deformation. So that means the standard test specimen is attached to that machine, that is called UTM machine. Load is applied over the specimen, and at various load points we have measured the deformation. Now we know the deformation and load. Also initially we have taken the diameter D as well as L0. So we can find, once D is known, we can find the initial or original cross sectional area is equal to pi by 4 D square. Okay, so what is the stress developed at various points? Stress is equal to, we can find P1 by A, that will be, say it is given by sigma 1. Similarly at this loading point, that is loading point P2, we can find sigma 2 is equal to P2 by A, and at loading point P3, say sigma 3 is the stress developed is equal to P3 by A, and at last that is say sigma n is equal to Pn by A. So at various loading point, what is the stress developed we have calculated. Now similarly we can calculate what is the strain developed at various loading point. Say at this point the strain, say epsilon 1 is given by dl1 by L0. At this point epsilon 2 is the stress developed is given by dl2 by L0. Similarly epsilon 3 is given by dl3 by L0, and at the breaking point strain developed, say it is given by epsilon n is equal to dln by L0. So that means in this UTM machine at various loading points, say P1, P2, P3 dot Pn, we have calculated stresses and strains separately. So that means we know the stress and strain at various loading point. Now if we plot these stress and strain value on a graph paper, so let the test, first test what is carried out for a ductile body like mild steel. So we are considering mild steel because the enormous use in the industry. That's why we are taking the mild steel for the analysis of simple tension test. So specimen of mild steel, standard test specimen, it is tested in an UTM machine, and at various loading point we have calculated stress and strains. So this side, if we stress, and this side we will plot, that is strain. So if we plot the stress versus strain on a graph paper for mild steel, so the curve will be somewhat straight line up to some point. After that the curve will slightly bend from straight line, then the curvature will be more, and after that the curve will go down slightly, then there will be a sawtooth type formation, and thereafter the curve will rise and ultimately the body will fail at this point. So this almost similar shaped curve you will get for a mile steel. Now there are various points we will discuss from here, that is, what is proportional limit, what is elastic limit, what is upper yield point, lower yield point, what is general yielding, what is strain hardening, then ultimate tensile stress, then what is necking and the breaking point. From this graph, so the first point up to we say the curve is started from origin O, and it indicates that the curve is started from origin O. It indicates that this is a virgin specimen, so it is not used before for any testing purposes. Okay, so it means it is started from this origin, and the first point up to which the curve is a straight line is denoted by point P, and P is called point of proportionality or proportionality limit point. So up to this point P, the stress is directly proportional to strain. Okay, so Hooke's law is obeyed up to this point. This point P up to which the curve is a straight line, this point P is known as a point of proportionality, and up to this point the body obeys Hooke's law. Okay, and the corresponding stress is given by, that is, sigma P, that is proportional limit stress. Now if we increase the load, the curve will deviate from straight line but slightly, and that point is called elastic limit point and is denoted by E, and corresponding stress is called elastic limit stress. So point E is known as elastic limit point, means body is fully elastic up to this point. So if the load, external deforming load, is removed from this point, then body will come back to its original shape and size. No permanent set will present in the body. But beyond this, if we load the body and after removal of external load, there will be some permanent deformation present in the body. Now if we load the body beyond this point, so we will get this point, that is called upper yield point. What is this? Is known as upper yield point. So corresponding stress is given by sigma y, upper yield point stress. So this is the upper bound condition or upper limit. If we cross this limit, then further phenomena will happen, otherwise this phenomena will not take place. So if we cross this value, that is sigma y limit or sigma y into original cross sectional area, that much load if we apply over the body, beyond that, then only the further phenomena will take place. So it is seen when this upper bound is crossed, so the material body will deform or yield at much lower stress value than this upper yield point. This point is known as lower yield point. So why I will come? Thereafter we will see a sawtooth type formation here, and this is known as general yielding. General yielding. Once the general yielding is over, the stress required for further deformation or load required for further deformation increases from this point to up to this maximum limit point. So if we see, the stress required in this is increases, and that is because of some phenomena is called strain hardening phenomena. Strain hardening. Because of this strain hardening phenomena, the stress required for further deformation increases. And this is the maximum stress which is seen in this curve, and this is called the ultimate tensile stress, that is sigma UTS. Thereafter, here at this point, some phenomena is taking place, is called necking. Okay, and ultimately the body will fail here, failure point. So we have seen so many points here. First point is the proportional limit. Up to the proportional limit or up to point P, the curve is a straight line and Hooke's law is obeyed up to point P. The reason is, as per Hooke's law, stress by strain is a constant and is given by, say, E. Linear stress to linear strain, that is equal to E, Young modulus of elasticity. This is a straight line equation. Now, if you see, from beyond point P, if we load, the curve is deviated from the straight line. So, the line is a curved line, hence it is not valid. So, that means Hooke's law is obeyed up to point P or point of proportionality. But the body is fully elastic up to point E. So, up to point E, if we remove the load within point E, then the body will come back to its original shape and size. But beyond point E, if we move, then the body will not come back to its original position. Some permanent deformation will remain in the body. Now, this is the upper yield point, this is the upper bound condition. If we cross this position, then further phenomena will take place, otherwise further phenomena will not take place. So, if we cross this sigma y value, it is seen that at lower stress value, there will be appreciable deformation in the body. This is because in every solid body, there are thousands of defects. The defects starts moving as soon as this upper bound condition is exceeded. Thereby, a lower load is required. So, at lower load, the body will deform and the deformation will take place at every cross section of the body. That's why it is called general yielding. Yielding means deformation. Okay, this sawtooth type curve is because of the movement of the defects in the body. Once the defects moved, thereafter, for further deformation, we require a higher load or a more load is required. More load is required after this point is exceeded. And this phenomena is called strain hardening. What is strain hardening? Consider a body. Now you apply the energy over this body. So for the sake, you consider a wire, metal wire, metallic wire. Then you apply the load over this wire. Then after some times, 3, 4 or 5 times, you will find that more energy is required for bending that wire. So that means whenever we are applying energy over a body, some of the energy is absorbed by the body and it is not relieving. So thereby the body becomes stronger. So that means this is the phenomena taking place after the general yielding is over. So that means body becomes hard because of strain hardening phenomena. Thereby the load required for further deformation in this zone increases. And ultimately, this is the maximum stress which is seen in the graph, that is called sigma UTS. That is the actual strength of the body. This is the maximum resistance offered by the body before failure. So sigma UTS, it is expressed in stress term, that is the actual strength of the body. But in mechanical engineering, we are considering sigma Y as the actual strength of the body, because if there is any permanent deformation takes place in the body, then as per our consideration, that body has failed. So that's why sigma Y we are considering as a strength of body in mechanical engineering, but actual strength is sigma UTS. And at this point, one phenomena is taking place, that is called necking. What is necking? So as per our assumptions that the body is a slender bar, that means all the cross sections of the bar are same between that gauge length, all the cross sections are of equal size, but theoretically it may possible, but practically it is not possible. So that means some area may be slightly less than the surrounding area. Once the area is slightly less, say this area is slightly less than that of the surrounding area, what will happen? The stress developed in this section will be more, thereby this portion will elongate more, and thereby again it will decrease in size, and only this portion will carry on increasing and the other area will not deform at all. So thereby the necking takes place and the area supporting the load reduces. So when this area is not able to support the load, so that time the body will fail. Okay, so this is actually this will fail. So we have seen the stress strain diagram for a ductile body like mild steel, and the shape of the curve is like this. Up to point P, body the curve is a straight line. After that it will slightly bend up to point E, and after that a more bending, that is we will get sigma Y. After that we will get lower yield point, general yielding, strain hardening phenomena, upper yield point, necking, and ultimately the fracture point. So we have seen here some important points like proportional limit, elastic limit, modulus of elasticity. What is modulus of elasticity? So this is the modulus of elasticity. It is the ratio of stress to strain within elastic limit. Stress to strain, the ratio of stress to strain is called Young's modulus of elasticity. Now this is the yield strength, upper yield point. What we are telling this one as yield strength of the body, upper yield point. We are taking this one as strength of the body for design of ductile materials. Next, the ultimate tensile stress. This is the ultimate tensile stress, and this is the actual strength of the body. Next is the, we will see what is called modulus of resilience. What is modulus of resilience? Say this is point E. If we load up to point E, the energy absorbed by the body is given by the area under stress strain diagram up to point E. So stress applied is sigma E. Let this is the epsilon E. So this triangular portion area, energy absorbed by the body up to elastic point, up to elastic limit per unit volume is called modulus of resilience, and it is given by half into sigma E into epsilon E. That is the modulus of of resilience. Another important point what we know from here is modulus of toughness. Modulus of toughness. So now if we see the energy absorbed by the body per unit volume up to failure point is given by the area under stress strain curve up to failure point. The area under stress strain curve up to failure point. So if the average stress is given by sigma average, then it is given by sigma average into strain at failure point, say epsilon f. So that means the area is given by sigma average into strain at failure point. So this is the area. So per unit volume this area gives the energy absorbed by the body up to failure point, and this is called the modulus of toughness. Now we will see two more terms, that is percentage elongation and percentage reduction area. Percentage elongation and percentage reduction area. Percentage elongation. Say the body is tested and the original length or the gauge length of the body was L0. So before testing and at breaking point, say the length of the specimen becomes LF. So L0 was original length and LF is the final length or the length at the breaking point. Then what is the change in length? LF minus L0 per unit length, it is LF minus L0 by L0 into 100%. That is called the percentage of elongation. That is change in length per original length expressed in so change in length per unit original length expressed in 100% terms, that is called percentage of elongation. So what is percentage of elongation? That is given by LF minus L0 by L0 into 100%. The LF minus L0 is the change in length divided by L0 per original length into 100%. That means change in length per unit original length expressed as percentage is called percentage elongation. Similarly, percentage reduction in area. Say original area of the specimen was A0, it was given by pi by 4 into d square, and say at failure point the cross sectional area is AF. Naturally AF will be less than that of the A0 original area. Final area will be less than the original area. So change in area, that is equal to A0 minus AF per unit original cross sectional area is given by A0 minus AF by A0 into 100%. So the definition: change in cross sectional area per unit cross sectional area expressed as percentage is called percentage reduction in area. These two terms are very useful for measuring a body, whether it is ductile or brittle. So if percentage of elongation or reduction area is less than 5%, if it is less than 5%, then the body is a is a brittle body. So a body whose percentage of elongation is less than 5%, the body is a brittle body, like cast iron also will fall here. And if the percentage of elongation is more than 15%, then the body is a ductile body. Now one more definition, we will see what is called the stiffness of a body.